we're going to do something similar with, and there is something similar with NVIDIA as well.
Okay.
It's a little more obvious, I think, with the ATI cards because it shows up as an icon on your desktop. For instance, that one has to that you could run fully at home. But I think it's hard to know with these collaborations what will happen and what will not, and so I don't like to talk about things until they're fairly far along. But it's definitely something on our minds.
Something that you think about anyway. Yeah, that's great. Also, next question up on my list here. What is going to happen with folding at home as far as the science end of things? Is simulating folding, but other aspects of biology here. Once you reach, say, 100 petaflops, I know that's far into the future, but I know some people have speculated in some forums here and there that you'll be able to simulate entire organelles within a cell. Molecule by molecule. Is that something 100 petaflops could accomplish?
That's a really neat question. I should admit I haven't thought that far out. I've been sort of thinking on the what would we do with 10 or 15, which is sort of we're about to hit 5, which about alone we're pretty happy with. I think as I don't want to daydream too much and sort of count chickens before they're hatched.
Yeah.
But it's fun to think about what could be possible. I think where all of this is certainly leading to is sort of is a molecular understanding of disease. And that's something that I think is very exciting because in other areas of my lab, when we do drug design, it is very much not quite as sort of as rationally designed. It's something where you have to do experimental screening or other things where you don't really know the answer. You're looking for the needle in the haystack with really good ways to search for it. And I think what's exciting about what can be done computationally is finally the rise of a much more rational approach to drug design.
Okay, yeah, and a molecular approach to disease.
Exactly.
Right. Okay, and that brought up another question. Yeah, 100 petaflops, still a long ways off. Oh, I wanted to mention that a lot of the folding teams out there I know do get excited by speculating at what can we do with 10 or 20 or 50 petaflops. So I think that type of talk garners more enthusiasm as well for all.
Yeah, no, I think it's a really exciting question because it's sort of talking about the future, probably talking about the next 10 years.
Yeah, that's right.
And I think one of the exciting things is that Moore's law basically was the hope that the speed of something would double every year and a half.
Right.
It's interesting that Moore's law is largely dead for, let's say, the speed of a single processor, but yet folding at home is outstripping the old version of Moore's law.
It's increasing at a greater pace than Moore's law, is what you're saying.
Yeah,
as far as computational
largely
ability.
due to a combination of effects where we're talking about adding more computers alone help speed up folding at home. But the other aspect is moving to platforms like GPUs and the PS3. That's a platform that probably is still speeding up, and probably speeding up faster than Moore's law. GPUs probably double in speed every year, rather than a year and a half.
I would say that's from what I've seen, that is a correct estimate. Now, I mean, obviously we're talking about 10, 20, 100 petaflops. We're dreaming a little bit here, and of course that dream comes with some increased technical problems. And I did watch a recent presentation of yours about how Stanford isn't going to be able to handle all of the data at some point in the future, the bandwidth, the data that is going to come with all of these petaflops. And you mentioned that you're hoping to start something called storage at home. Well, who knows if that's going to be the final name of it, but storage at home, a kind of a peer-to-peer storage and calculation at end-user computers, and kind of calculating in the cloud. How soon are you to launching that type of an effort?
Yeah, I think that's a really good question. For years we've been looking at how things are scaling, and one of the biggest challenges we have server side is to try to just handle and manage and bring in all these servers and do so in a reliable way. And that's, we've grown so quickly that that's always been an issue for us. Also balancing sort of server issues with pushing science and things like that. I think we've actually gotten with sort of a revamped backend that we've just been writing over the last 2 years. I think we're actually going to scale pretty well for the next year or two, but looking longer than that, let's say 5 years or 10 years, that's where I think bandwidth really will be a killer. And so about a year and a half or 2 years ago, Adam Bieberg in my lab and I started talking about this possibility, and Adam has a first author paper out on sort of the basic idea behind storage at home. That came out probably over a year ago, and he's been steadily working on developing the sort of all the code related to the project.
Okay.
And it's something that I think would be exciting, because one of the great excitements about a distributed computing project is when lots of people join the project. But one of the great challenges is that as more people join, it becomes just a huge server challenge.
Right.
And so the idea here is with storage at home, as more people join, hopefully we'll essentially get added server performance as well, since everything essentially will be out in the cloud.
Yeah, and it's just amazing for me to think about how, 10, 20 years ago and supercomputing and how it all worked, and now, the storage, the calculations, the research, it'll go on out in the cloud, not at a central location. It's fascinating to me.
Well, it's kind of neat to think about is that right now with fully at home, the calculations are being done on the cloud. So the only thing that's not done there is sort of storage and analysis. And right. So in a sense, a lot of the hard part is already there. So why not just move the rest?
Just move it all out there, right? And that does bring up another question that I had asked ahead of time before the show about someone wants to know, they're running fully at home on their computer and they do one work unit. What actually have they just done? What would one work unit typically represent?
So I think it varies from calculation to calculation, but what's going on in most of these work units is that you're solving a small part of watching how a protein would move or a drug molecule would move with that protein.
Just like 1 nanosecond of one particular fold of one part of one protein.
Yeah, or if this was a GPU work unit, it might be like 100 nanoseconds or 200 nanoseconds.
Okay.
But so some amount of time that is relatively small compared to human time, but still relatively large compared to what how fast it takes a computer to get things done. Typically it takes a day to get a nanosecond done. So
sure.
I mean, that's what's exciting about these GPUs is that they can get hundreds of nanoseconds done per day.
Yeah, they're blazing speed. It's amazing how much it's a supercomputer in your desk.
Yeah, absolutely. And so one part of that is, one part of this puzzle. It's sort of shedding light on one area. And, one work unit is important, but it's sort of like a snowflake or like one light. One thing is useful, but it's when we have thousands or millions is when the game really changes.
Sure. Okay. And then that. Speaking of calculating out in the cloud, getting back to that question, will there now out in the cloud? Obviously, it's going to be redundant, and it's very speculative. The data has to be redundant, and it's very speculative at this point. But will there be some sort of critical backup of some key data at Stanford yet? Yeah. Even as you move out into the cloud.
I think there'll have to be. I think part of what's interesting about the way we want to organize this is that normally you think of calculation and storage being two separate entities.
Right.
But you can start to blur the two a little bit. Because what we can do is that we can calculate something and store, let's say there's 1 million steps in the calculation. We could store all 1 million steps. Or we could store, let's say, every 1,000 steps and say that, well, if we wanted to get, let's say, from step 5,000 to step 6,000, we start at step 5,000 and just recalculate the next 1,000 steps. And so what it turns out is that you can actually blur some of the aspects of calculation and storage such that for a little bit of calculation, you could recover a lot of storage space. And so hopefully in the long term, what we'll be able to do is store everything out there, but the most critical pieces, these so-called checkpoints, would either be stored at Stanford or would be stored with lots and lots of copies, such that if we had to recalculate something, it wouldn't be that you'd have to wait. You'd have to redo everything.
Right.
Yeah, you could redo the key parts very quickly. And so I think that's going to be really neat, this blurring of those concepts. And in some ways, you can think of compression as something that blurs storage and computation.
Yes.
That, you can gain some more storage, a little bit of computation. This is sort of like, compression on steroids.
It's kind of like a lower resolution copy of
yeah, exactly, and then we can sort of we can retrieve, just recalculate the higher res version whenever necessary.
Okay, I've got another question here that was asked before the program, and that is about CASP competitions. Are you familiar with the CASP
yes.
programming competition? And has your team or any teams involved with Folding at Home ever entered some of those competitions?
Yeah, we've never entered CASP on our own. We've actually consulted